video, we will be covering the 2009 AP Calculus BC Free Response question number 6. The topics covered will include Taylor and Maclaurin series, the ratio test, concavity, and points of inflection. The question states the Maclaurin series for e to the x is e to the x equals 1 plus x squared over 2 plus x cubed over 6 plus x to the n over n factorial. The continuous function f is defined by f of x equals e to the x minus 1 squared minus 1 over x minus 1 squared for all x such that x is not equal to 1 and f of 1 equals 1. The function f has derivatives on all orders at x equals 1. So looking at part A, we are asked to write the first four non-zero terms and the general term of the Taylor series for e to the x minus 1 squared about x equals 1. So we are given that the Maclaurin series for e to the x is x to the n over n factorial. So all we have to do for this part is plug in x minus 1 squared into the series to get 1 plus x minus 1 squared plus x minus 1 to the 4th power over 2 plus x minus 1 to the 6th power over 6. And our general term, just plugging in x minus 1 squared, is x minus 1 to the 2n over n factorial. Part B states, use the Taylor series found in Part A to write out the first four non-zero terms and the general term of the Taylor series for f about x equals 1. So we can see that f of x is defined as e to the x minus 1 squared minus 1 over x minus 1 squared. So looking at our result from Part A, we can see that the first four non-zero terms for e to the x minus 1 squared were 1 plus x minus 1 squared plus x minus 1 to the 4th over 2 plus x minus 1 to the 6th over 6. Those are the first four terms. So we can plug that into f of x, as you can see here. So I've plugged it in right here. And then f of x again was e to the x minus 1 squared minus 1 over x minus 1 squared. So this is the equation plugged in. And then after simplification, we can see that we get 1 plus x minus 1 squared over 2 plus x minus 1 to the 4th over 6 plus x minus 1 to the 6th over 24. And if we're looking at a general term, we can either go with x minus 1 to the 2n minus 2 over n factorial or x minus 1 to the 2n over n plus 1 factorial, and both will yield the same result. Part C asks us to use the ratio test to find the interval of convergence for the Taylor series that we found in Part B. So we can see the Taylor series found in Part B was 1 plus x minus 1 squared over 2 plus x minus 1 to the 4th over 6 plus x minus 1 to the 6th over 24. And a general term could be x minus 1 to the 2n over n plus 1 factorial or x minus 1 to the 2n minus 2 over n factorial. And again, the ratio test is the limit as n goes to infinity of a to the n plus 1 over a to the n set to some value p. If p is less than 1, then the series will converge absolutely. If p is greater than 1, then the series will diverge. And if p equals 1, the test is non-conclusive. So if we use the general term x minus 1 to the 2n over n plus 1 factorial, what we can see using the ratio test is that you substitute the n for n plus 1. So in green here, you can see that 2n becomes 2n plus 2, n plus 1 factorial becomes n plus 2 factorial, and then you multiply by the reciprocal of this. And simplifying, you get x minus 1 squared over n plus 2. And so if we take the limit of that, we get 0, and therefore the interval of convergence is from negative infinity to infinity because of the n right here. So if there's an n in a denominator, that typically means that the interval of convergence will be from negative infinity to infinity, or encompassing all real numbers. This is because the limit of a number over infinity is 0, and by the ratio test, 0 is less than 1, which indicates divergence. So lastly, Part D states, use the Taylor series for f about x equals 1 to determine whether the graph of f has any points of inflection. So in order to do this, let's first look at our function f of x and the general term, which was x minus 1 to the 2n over n plus 1 factorial. And then the first step I did was take the first derivative, and in doing that, I got x minus 1 plus 2 times x minus 1 cubed over 3. And the general term was 2n times x minus 1 to the 2n minus 1 over n plus 1 factorial. And then the next step I did was I took the second derivative of this, and in doing so I got 1 plus 2 times x minus 1 squared with the general term of 2n times 2n minus 1 times x minus 1 to the 2n minus 2 all over n plus 1 factorial. So therefore, since every term of f double prime of x is non-negative, as you can see here, f double prime of x is greater than or equal to 0 for all x, or it's concave up for all x, and therefore it has no points of inflection. So a brief refresher of inflection points from Calc B. Inflection points occur when the function changes concavity. So concave up corresponds to a positive second derivative, and concave down corresponds to a negative second derivative. So when the function changes from concave up to concave down, or vice versa, meaning the second derivative changes signs, then the second derivative must equal 0 at the point where it changes from concave up to concave down. So that would be the point of inflection. And another way to find this is if you look at the first derivative, you can see where it changes from increasing to decreasing. But in this case, in both terms are strictly increasing, so we can conclude that it has no points of inflection. Taylor series usually occur on the number 6 question for all free response AP Calculus tests. So it's nice to remember a few Taylor/Maclaurin polynomials for use because they might not always be as nice as they are here and give you the Maclaurin series for e to the x. So some key ones that you should remember is that the general term for a Taylor polynomial would be f of a plus f prime of a times x minus a plus f to the nth power of a over n factorial times x minus a to the n. And then a quick review of Maclaurin polynomials. So if you get 1 over 1 minus x, the series representation would be x to the n. And again, you could manipulate it like 1 over 1 plus x would be negative x to the n. Sine x is negative 1 to the n times x to the 2n plus 1 over 2n plus 1. The series representation for tan inverse of x is negative 1 to the n x to the 2n plus 1 over 2n plus 1. The series representation for e to the x was given in the question as x to the n over n factorial. The series representation for cosine x is negative 1 to the n x to the 2n over 2n factorial. And the representation for ln 1 plus x is negative 1 to the n minus 1 x to the n over n. And again, it's just really helpful to know these, especially for the multiple choice and for the number 6 on the free response, as it's usually a Taylor or Maclaurin polynomial. If we look at the scoring guidelines, we can see that for Part A, where we were asked to write the first 4 non-zero terms, we were given 1 point for writing the first 4 terms and 1 point for the general term. For Part B, similarly, we were given 1 point for the first 4 terms and 1 point for the general term. So for Part A and B alone, you got 4 points out of the 9. So even if you didn't know how to do Parts C and D, just by answering Parts A and B, you're already above the average for this question. For Part C, we were asked to use the ratio test to find the interval of convergence. And so 1 point was awarded for setting up the ratio. So as you can remember, the ratio was given here. So for setting up this, you got 1 point. For computing the limit, as you can see here, you got another point, and then you got 1 point for your answer of the interval of convergence. And then lastly, for Part D, you were asked to find this Taylor series of f to determine whether f had any points of inflection. So for that one, you were given 1 point for finding the second derivative, as you can see here. And then you were given 1 point for your answer that has no points of inflection.